today we're kind of in for a bumpy ride, I suppose.
Yeah.
If we do have an earthquake during the talk, just duck under your chairs. This is an 1887 station, but it has survived the 71 earthquake in 94, so hopefully we'll be okay. Our speaker received a Bachelor's of Science degree in astrophysics in 1969 from Indiana University and a PhD in astronomy in 1975 from the University of Texas at Austin. And he should know that I actually graduated from the University of Texas Southwestern Dallas Medical School, so we have that in common. He's senior scientist at the Aerospace Corporation, where he specializes in infrared spectroscopy of comets, novae, supernovae, young stars, and very old stars. He has held research positions at Caltech, UC Berkeley, and the United States Geological Survey. He's published over 150 scientific papers and 10 books, much of it based on observations from telescopes in Mauna Kea in Hawaii, Kitt Peak, Mount Hamilton, and in space. He also works with the U.S. Geological Survey on plate tectonics with a focus on the southern San Andreas Fault, and author of the book which is being featured today and which will be on sale after the show and can be autographed, called The Field Guide to the San Andreas Fault. So it is my pleasure and honor to introduce Dr. David Lynch.
Thank you. Well, first of all, thanks for coming. I want to echo what was said before. It's a great day outside and you're inside. And also I've got a bit of laryngitis and my normally deep, manly voice has turned into this. So you're gonna have to put up with it. Let's see, the other thing is, when you leave here today, you're gonna know more about the San Andreas Fault than almost anybody in California, okay? Because everybody's heard of it, and they kind of are afraid of it, but they're kind of not, but nobody knows where it is, what it means, if they should worry, if they should not worry, and believe me, you shouldn't worry too much. So that's the main thing. I'm just going to tell you about the fault, how to see it, and all of that. So with any luck, the computer will wake up, and I'm going to show you where the local faults are around Santa Clarita before I start talking about the San Andreas Fault proper. Anyway, here's, you know where you are, right? You're right here. What we have up here is the San Andreas Fault, but you notice it's not just one line. Okay, it's many closely spaced lines, and that's important to realize. We think of the fault as being a narrow crack in the ground and you can hop from one tectonic plate to the other. That's wrong, you can't do that. It's really a fault zone. The nearest fault to you is this greenish thing right here, which is the Sierra Madre Fault. And the only faults that I've shown on here are the active faults. There are many other faults in the area, but they're not active, okay, that we know of. So for the LA Basin and all that, you're maybe 20 miles as the crow flies from the San Andreas Fault, and that's reasonably close. Okay, so San Andreas Fault. The way I got interested in this fault, I've always been a rock hound, probably like many of you. So I always liked going outside and playing in the dirt and all that kind of stuff. And I was driving back from San Francisco once. I just picked up a new car. And I didn't want to rev the engine too much because it's new, right? At least the new, I don't know if that's true now, but it used to be true a long time ago. And so I said, I know, I'll just drive from from San Francisco to LA. I'll drive along the fault. And I didn't even know where the fault was, but I kind of knew where it was. So I drove along all these back roads, and it was so interesting. I saw this great stuff, and I said, I got to learn this. So I went to the internet and figured there must be 1 million books on the San Andreas Fault. Turns out there's not one, okay? There's lots of earthquake books and all that kind of stuff, and there's a few books that talk about the San Andreas Fault, but nobody really shows you where it is, what it means, what to look for, and all that. So I said, okay, I'll write it. So I did. So first of all, where is the fault? Well, we're kind of right down in here somewhere. Actually, we're down here. The fault starts down by the Salton Sea, and it does begin. There is a beginning to the San Andreas Fault, a physical terminus. Comes up through Desert Hot Springs, San Bernardino, Palmdale, Fraser Park, goes through the Carrizo Plain, through Parkfield, up into San Juan Bautista, and then it goes up to Daly City, and then it goes offshore in Daly City. In fact, the San Andreas Fault does not go through San Francisco. It doesn't even enter San Francisco County, but it's close enough. So it goes offshore, comes in at Point Reyes, up through Point Arena, and may or may not touch Point Delgada, and then it turns left and goes into something called the Mendocino Triple Junction, and that's where it ends. So the fault really does have a beginning and the end, and I'll talk a little bit more about that. And the entire San Andreas Fault is within California. The fault itself is a registered natural landmark, okay? And this wonderful black brass plaque is, well, I'll show you where it is. It's inside this building. And in fact, the fault runs right through this building and it's ripping the building apart. This is Alan Pat DeRose. They make good wine, but you don't get to see the plaque unless you buy wine and ask. Okay? Most people don't even know it's there, okay? But it is. And by the way, on a lot of these pictures, you're gonna see coordinates, GPS, latitude and longitude. And that's, in the book, I've got hundreds of those, so you can't get lost. Well, you can't get lost. I've got lost lots of times. Now, to look at this on a bigger scale of things, the Earth is covered with these plates, thick, stiff, rigid plates, or almost rigid. They float around. They literally float because they're made of rock that's less dense than the deeper mantle rock. And so here the different colors show the different plates. And the Pacific plate is right here. It's moving this direction. And here's the San Andreas Fault right here. Okay? So the San Andreas Fault is only a very small part of the plate boundary that the Pacific plate has. And so it's just there. And I said it's moving that way, and that's because this cuts California. There's a bit of California in here. Let me see, where are we? We're on the Pacific plate. Yes, we are. So we're moving northwest, kind of towards San Francisco, at about 2.5 inches a year, okay, on average, which is about as much as your fingernails grow, okay, every year. So that's how fast we're moving. Now that's on average. Most of the time it doesn't move at all. It sits there, it's stuck, okay, and it builds up stress and it deforms the rock, and then the rock breaks and we have an earthquake. So this is the big picture. Here's a little close-up of it. Here's the San Andreas right here, and you see it does end right there. Now, when I say a plate boundary, it can be very complicated. The plate, what happens at the San Andreas Fault ends, there's an area called the Brawley Seismic Zone that hops over to the Imperial Fault, which crosses the Mexican border, which then hops over to another fault called the Cerro Prieto Fault, and that goes down into the Sea of Cortez, and it's a bunch of little stepping faults all the way down. The reason the Baja Peninsula is this long, skinny thing that's separated from mainland Mexico is because about 5 million years ago, the plate boundary was in Mexico, and it started pulling, it grabbed part of what we call Baja now, and started moving it away at about the same rate. So the Sea of Cortez is opening up at a very slow rate. So here's the fault, goes up here and goes into the Mendocino fracture zone. North of here, and this is the plate boundary up here, right here we have a subduction zone. And a subduction zone is a place where one plate is moving under another plate. And that's where the big earthquakes and that's where volcanoes are. All the big earthquakes you know about, the Chilean earthquake, which was big. The one in Indonesia in 2004 that made the big tsunami. These are all on subduction zones. So that's where the big earthquakes are. The San Andreas Fault is not a subduction zone. The plates, one plate is not sliding under the other. They're sliding past each other. I'll talk about that. So the San Andreas cannot make these huge earthquakes, okay? But believe me, it can make big earthquakes. Just not the biggest ones. Okay, so first of all, what is a fault? Okay, a fault is a very simple concept, really. It's a crack in a rock along which there's been motion. A regular crack in a rock is just called a joint, but if it cracks and moves, it's called a fault. And there are jillions of faults, okay? Many faults are even microscopic. Here's a fault I found in a rock. It's very easy to see that this part here has been offset from the lower part. So I took and chopped the picture in half and put them together to show how it used to be, okay? But this is just a small fault. It doesn't have a name, it's not important. What makes the San Andreas Fault more interesting is that it's a plate boundary where you have these two huge land masses moving. Most faults are little and you don't have to worry about it. Break a cookie and you have a fault. So we live in a three-dimensional world. So if you have two plates like this, They can move in three ways. They can go up and down. Okay, that's called a dip-slip fault. They can go side by side. That's called a strike-slip fault, and that's what the San Andreas is. Or they can open up or close up. So there's three ways that chunks of rock can move. The San Andreas is a strike-slip fault or a lateral fault. Now, you can have two kinds of plate motion. If it's lateral, they can move this way or they can move that way. The San Andreas is a right lateral transform fault. And what that means is that if you stand on one side of the fault, imagine it's a line, it goes like that, and you put somebody right in front of you. If you wait long enough, they will move to your right. And that works no matter what side of the fault you're on. Okay? So the San Andreas is a right lateral transform fault. And there's a bunch of other faults. This is a particularly interesting one because this is what made the Northridge earthquake. Okay, it's called the blind thrust fault. And what that means is that it's at a very shallow angle. Many fault planes are vertical, but here it's at more than 45 degrees, and it does not touch the surface. It did not reach the surface. That's why it's called blind. And so we did not know about the Northridge fault until the Northridge earthquake. And so there are many thrust faults in the area, but if they don't reach the surface, we usually don't know about them. And this is probably one of the most important slides I want you to look at. Faults, we think of them as a line, and they are, but they curve a little bit, or they twist. And curves in a fault, or steps in a fault, have enormous consequences for the landforms that they make. And I have some expensive visual aids right here. Go like this. So here's the Pacific plate, all right? Here's the North American plate. The fault's more or less at 45 degrees. And so the Pacific plate wants to move this away, all right? So what happens? If you have a right-hand step in a right lateral transform fault, what happens? It opens a hole. It opens a depression in the ground. Okay, those are called sags. And if they fill up with water, they're called sag ponds. Now that's important. What about if you have a left-hand step? So now that wants to go like this and it can't. It runs into the other plate. So what happens when two plates come together and they can't, get around each other? They bend up. Okay, and that's called a pressure ridge. Okay, and so pressure ridges can be small, they can be large. They can make mountains. That's one way to make mountains, is actually have two plates come together and they bend up like that because they can't go anywhere else. So we'll be talking a lot about bends and faults. All right, so there you go. Well, I told you all this already. It's like two pieces of bread on a table sliding past each other. The gap in them, that's the San Andreas Fault right there. This is important. Even though the fault is a big crack in the ground, most places you can't see it. Okay, why? Because there has not been an earthquake in that part of the fault for a long time, and wind and erosion and everything just covers it up with the local soil. So in most places you cannot see the fault. Okay, so the trick to going and, quote, seeing the fault is learning the landforms that it makes, pressure ridges, sags, scarps, and other things like that. So that's really what I'm going to be talking about here is the landforms. Another thing that happens is to obliterate any evidence of the fault is you build a house on it. Okay? And there are many communities in California that are sitting right on the fault. So I'm going to take you on a couple of little trips from the book in Southern California. I'm not going to do them all by a long shot. Here's our San Andreas Fault. On all these, it's always going to be red. And the driving route to the book are in yellow. So you see the whole idea here was to drive as close as possible to the fault. In this area right here, I've drawn another fault. That's called the Banning Fault. And the reason it's there is because the San Andreas, or I should say the plate boundary, there's a curve in it. You can see that the fault is fairly straight right here, but once you get north of I-10, it starts to bend around. Okay, that's a restraining bend. And they're stuck, and so they want to go up, okay? And they do, they make big mountains. The two highest mountains in Southern California straddle the fault, San Jacinto and San Gorgonio. Okay, and they're there for a good reason, because of this bend in the fault. And it turns out that you can't follow the fault up through the San Bernardinos, so the driving route takes us along the Banning Fault. So here it is from satellite. Here's the Cerro Prieto Fault, Imperial Fault, San Andreas Fault right here. And one of the interesting things that happens is that down in Imperial County, very close to where the fault begins, there are 5 small volcanoes. Now, most of the big volcanoes you see, name a volcano. The big ones, like the Cascade Range volcanoes, those are all due to subduction zones. Okay, when a plate slides under another plate, interesting things happen and they make volcanoes. Down here, we don't have that happening. What's happening is that there's a left-hand step in the plate boundary, and that opens up a hole. It's called the Salton Trough. But that also exposes the mantle, this actual hot magma from down below. And so that oozes up through the crack, reaches the surface. And so there's these little tiny volcanoes. They're not active. They haven't been active in years, not in historic times at all. And they're not these big stratovolcanoes. And they don't erupt violently. You're just exposing the mantle a little bit and the magma comes up. And here's one of them. This is Obsidian Butte. This is right on the Salton Sea. And out there is all this beautiful flow-banded orbicular, or I should say vesicular, obsidian. It's just beautiful stuff. And here's something else they have down there, is mud volcanoes. Okay, mud volcanoes are very rare, okay? They don't happen very often. Mud pots, yes, boiling in mud pots like at Yellowstone and all that. But here we have a whole field of mud volcanoes, and they grow just mechanically the same way a big volcano grows. Hot mud gets shoved up to the surface by CO2, and it forms a cone, and then it builds up and builds up and builds up from the central vent, and you get a volcano. So they're 4 or 5 feet high, and they're real interesting. They have hot mud that bubbles in them. Okay, it's like a little Yellowstone. And here's one of the popping mud bubbles. Okay, you go down there and they go bloop, bloop, bloop. Now moving further north into the San Andreas Fault proper, this is down in Riverside County. This is Painted Canyon right here. The red line here is the San Andreas Fault. See this brown ridge that kind of runs along the fault? That's a pressure ridge. And that's right on the San Andreas Fault, or close enough to it. And then you can actually drive up here in Painted Canyon, and you'll see, that's the entrance to Painted Canyon. It's beautiful, all these different rocks. This is the pressure ridge from the San Andreas Fault. And you get up to an auxiliary fault. Remember in the very first picture I showed, the San Andreas has a lot of parallel cracks with it. Well, this is one of the parallel cracks. It's called the Painted Canyon Fault. And it's right here. And here's my truck for scale, right here. Now, this is the hallmark of a transform fault. You have different rocks on either side of the fault, okay? That's one of the first things people noticed when they started trying to understand this stuff. They found rocks that didn't belong together that were touching one another. And that's because rocks had been carried by the plate motion, and rocks from over here got pulled up here. The other thing to notice is this deep erosion, okay? All of this stuff here is something called fault gouge. And what happens is if you have 2 plates rubbing together for millions of years and having earthquakes, when you have an earthquake, the rock goes like that. Well, you do that with your hands get hot, right? Same thing. It grinds up the rock into a fine powder, it heats it up. Mechanically, the chemistry happens because it's so hot briefly. And you're left with this kind of powdery rock. Sometimes it's almost putty, it's almost sticky sometimes. And that's called fault gouge. And there are places up the San Bernardino Mountains where you can drive for 10 miles through fault gouge. Okay, you bet. It's in the book. So this kind of erosion pattern is something to look for. If you see this along the routes, this is fault gouge. Well, moving further north, and this is where it gets interesting. This is Palm Springs down here. This is Interstate 10 right here. And here's the fault right here. You can kind of see it. And also the Banning Fault, the one that splits off because of this stress in the rock, it's right here. Well, what do you notice? Well, you got flat land and then bang, all of a sudden you've got mountains. These are pressure ridges. Now, one interesting thing along here is you notice all these green areas. And that shows up best on the next one. And it shows a topographic map of the area. There's your fault. All these green areas. Okay? Now this is out there in hard desert. And yet there's standing water in places, and there's palm trees and grass and things growing right on the fault. And here you can see them. I took this picture here from an off-ramp on Interstate 10, looking north at the Indian Hills. Look at this line. That's where the fault is. And here's a close-up of one of the areas. You can see this is hard scrabble desert. There's almost nothing growing here. And yet, right along the fault, it's wet. Why? Well, there's underground water, and it's flowing toward the Salton Sea. And when it gets to the fault plain, where all this gouge is almost like flour in places, it blocks the water flow. And what does it do? It ponds to the surface. Okay, right here. This water wants to go this way, but it can't because of the fault gap. Ponds to the surface, and you get a green line. It's called vegetation liniment. Anytime in a desert you find water, there's a fault there. And Desert Hot Springs is a sitting duck. Okay, you can see there's your fault right there. And you can literally drive through town, and I've done it. You know, you just drive along and just look at all the fault features. Little scarps. A scarp is a long cliff. Think of it like a curve. It separates two horizontal areas with a nearly vertical face. That's a scarp, okay? And low scarps and pressure ridges all the way through Desert Hot Springs. Think about that. Desert Hot Springs. Hot springs. What do you know? Those hot springs are there because the San Andreas Fault goes right through town. So we can't get into San Bernardino's because the Morongo Indian Reservation keeps us out, and conservation groups keep us out, and oh, geez, it's too bad. But you can't, so you drive through Danny Fault, you come to Highland, California by San Bernardino. Here's the fault. Okay, there was a law passed, I don't know, 40 years ago, 30 years ago, that said you can't build a house within 100 feet of the San Andreas, within 100 feet of an active fault. Okay, and you think 100 feet. And I know people who said, no, I'm 200 feet from the fault, I'm fine. Wrong. So anyway, a lot of places were built before we knew about fault, and can't do much about that now. But I'd like to know what building inspector was paid off to do this, because it's just nuts to think you're safe if you're 100 feet from a fault. You're not. All right, so now we're going to jump north and get up to our neck of the woods here. Here's your San Andreas right here. Yellow line is the fault right here. And we're going to go up to Palmdale. We're going to start at a place called Blue Cut. This is Interstate 15 right here. The fault, the infamous San Andreas Fault, passes through the three major utility transportation corridors for Los Angeles. Goes through I-10, Banning Pass. It goes through Cajon Pass, I-15, and through Cajon Pass, I-5. Okay, so anyway, we're going to start here. We started at a very interesting place called Blue Cut, and I'll show you a picture of Blue Cut in a minute. Our route actually follows this dirt road up here, and one of the first things we find is Lost Lake. It's a sag pond. It's a long, these sag ponds tend to be elongated right along the fault because on geological timescales, these things are moving. So here's Lost Lake. You can go there and visit it. You can swim in it if you want. Now here's Blue Cut. This is looking southwest from Interstate 15. And over here we have a dark gray metamorphic rock called Pelona Schist. It's old, it's dense, it's dark, it's plutonic. It came from deep down in the surface and was lifted up. And right next to it, right across the fault, is the Cajon Valley Formation, which is a very recent sandstone from an inland sea, a shallow sea. Those rocks could not have formed together. Could not have happened. They were brought together. This Pelona Schist right here came from Arizona. Okay, and it goes as far up as Palmdale, actually. I have a piece of Pelona Schist right here, and I have a piece of the Cajon Valley Formation right here. Okay, this is sandstone. This is schist. They could not have formed together, and yet they're like that up at Blue Cut. Okay. And this is one things that geologists figured out a long time ago. Yes, these faults, whatever they are, move. So yeah, here, you can play with them. This just shows it a little bit better. Cajon Valley Formation right here, and you can see how dark and dense this Pelona Schist is. These rocks do not belong together. And speaking of sitting ducks, this is Wrightwood. This is the main drag in Wrightwood right here. And if you look up south of Wrightwood up on the hill, you see this big scar. Okay? That's from the Heath Canyon landslide. And that's in Pelona Schist. What happened was, back in 1942, they had very heavy snowfall in the area. And when the spring melt came, all this water got into the rock, and this is Pelona Schist, which is kind of a grainy rock. I mean, it's like wood, it has grain. And because this rock had been sheared and torn up and twisted and mangled for years and years and years, it was very porous. Water got into it, lubricated it, and this whole hillside came down and took out about a third of Wrightwood. That was 1942. They've had slides since then. And all this rock came down Sheep Creek Canyon out onto the Mojave Desert. That's dark for a reason. Those are chunks of Pelona Schist. It's been carried 25 miles out onto the desert floor. This is Highway 38, I believe, or this is 38. You come through. You can get fairly cheap land in this area right here. You're now heading northwest on the main highway through Wrightwood. You go over the hill, the summit, you drop down, you start going toward Palmdale, and you come to just miles of Pelona Schist. Well, Pelona Schist on one side. This is kind of greenish schist. It's ground up, that rock. And this is ground up diorite that came from someplace else. Notice the deep erosion patterns that's very characteristic of the gouge. Trees have a hard time holding on. It's forever falling because it's crumbling. On either side of the road, that road's right on the fault. And we get to Palmdale, and what do we find? We find two sag ponds. Palmdale Lake is a man-modified sag pond. And here's Una Lake, another one. Notice it's elongated along the fault too. Our routes we actually drive up here, over here. And you can see that the San Andreas goes right through the interchange of Avenue S and California 14. I mean, in many places we know where the fault is very accurately. In some places we don't really know where the fault is because it's been covered up and there hasn't been a recent earthquake. But this one we know pretty well. And it goes right through the interchange. This is just next to the road cut right here. Okay, this was all horizontal sediments laid down, okay, in a shallow sea. And you can see what the motion of the plates have done. It just twists and turns it. We think of rocks as being as brittle and that, but they're not brittle on a geological timescale, and you put enough pressure on them, they'll bend, they'll move. And so, you know, all this dipsy doodle right here, those are all horizontal ones. This is called the Palmdale Road Cut. It's famous among rock hounds and geologists, but you won't find a single Chamber of Commerce member in Palmdale talk about it. Real estate people don't talk about it. It's the best known secret in Palmdale, is the famous road cut. All right, so now I'm going to take it. We're not going to do the whole trip here. We're going to go from Palmdale up to Fraser Park. And I just want to show you a couple of interesting things along here. Caltrans has been kind enough to tell you where the fault is by painting a double yellow line. Right where the fault is, okay? The road goes right along the fault for miles. Next, please. And we get up a little further and we come to Lake Hughes and Munch Lakes. Gee, look at that. Sag ponds right along the fault. Elongated right along the fault. Go to Bushnell Summit where the road tops out and goes down. Do you recognize all this? That's gouge. That's gouge. The fault's up here about 100 meters. Fault zones can be very wide or very narrow. In this case, the fault zone is fairly wide. Now, this unremarkable picture right here is actually fascinating. This is a type of rock called rhyolite. And about 10 million years ago, this big volcanic area, the plate boundary jumped. Okay, and plate boundaries move, by the way, and it carried the southern half north, and it became Pinnacles National Monument. So Pinnacles National Monument started out 10 million years ago, or 11 million years ago, in Los Angeles County. So anyway, that gets us up to Fraser Park, fascinating place, fault goes right through town. And then we go, oh, you're from Pine Mountain Club. Who's from Pine Mountain Club? Yeah, fault runs right through Pine Mountain Club, you know that. But I'm going to skip that, and we're going to go to really the best place to see the fault. You want to see a crack in the ground? This is it. This is one of the few places you could actually see this giant crack. It's the Carrizo Plain. And it's so interesting up there. This time of year, wildflowers are amazing. I have two routes. I have the regular tourist route, which anybody can do. And then I have the fun route, okay, where we go and cross the fault a bunch of times. Okay, so here's a picture I took a few years ago. Is there any question about something interesting happening here? This is called the Elkhorn Scarp, and it's a combination of a scarp and a pressure ridge. Even though the plates are moving mostly horizontally, there's always a little bit of motion in the other direction. It can go up, it can go down, it can go sideways. So it's mostly a transform fault, but there are places where there's bends and they move this way. It's a pressure ridge right here. And the fault zone's fairly narrow here. Our route actually comes up through here, goes into here, and we wiggle around and go up here. We'll talk about this area right here because it's real interesting. Here's a topo map with San Andreas Fault on it. This is called the Elkhorn Scarp. It's also called the Dragon's Back. The reason it's called the Dragon's Back is because it's a long pressure ridge, so it's long and skinny, but erosion has eroded these deep valleys at almost regular intervals along the back, so it's sort of crenellated like a dragon's back. Here's your dragon's back. Here's your fault. So this is the Elkhorn Scarp. Here's the San Andreas Fault. These mountains back here, this is looking northeast toward Bakersfield. These mountains here are called the Temblor Range. Temblor is Spanish for shaking. So now, we're now looking kind of down and southeast. Our route actually comes up here, turns here, and then we come along here, and we actually drive up the arroyo, which is a lot of fun. I call this place Picnic Point because that's where I always stop to have lunch, because it's the only place in the Carrizo Plain where there's shade. And the next picture I'm going to show you, oh, by the way, here's your fault if you wondered where it was. And you can see this. You can just sit there and walk up this little gully, and that's the fault. The next picture I'm going to show you to give you a feeling for the scale of things is that one, right? I'm standing on the fault looking back at Picnic Point, and this is the end of the pressure ridge right here. Okay. Further north is a very famous place called Wallace Creek. And Wallace Creek is famous because it flowed, like many creeks do, across the San Andreas Fault. Came down here, hit the fault. There's a little pressure ridge, a shutter ridge that blocked the creek. And as the plates moved, in this jerky motion every few hundred years, it carried the creek with it. And then a big rain came along, probably flooded, ponded behind the fault, broke through the pressure ridge. And so right now, the fault comes down here, goes 110 yards this way, and then comes down here. This distance right here is about 110 yards, something like that. And you can do the arithmetic, 110 yards divided by 2.5 inches a year. That tells you when this part of the creek was back here. About 3,800 years ago. So this is happening real time, okay? This is historic times, things are happening. Here's another ancestral channel over here. So this is going on all the time. So now I'm standing up on the hill looking down at it, and here's the creek. Goes like this, goes like that. So Wallace Creek is really a fascinating place. And by the way, these offset streams or offset channels, there are, I was going to say thousands. Probably are, but there's certainly hundreds of them in California. There are so many places where creeks have flowed across the fault and they've been carried with them. In fact, that's one way that we actually learn how much the fault moves, is that we can measure the offset, and then if we dig down in and get material that we can carbon date, then we know when it was, and so we can get a slip rate along the fault. So offset streams are very useful geologically. Oh, here's more. I just love this because I found this all on my own. This is our route right here. Remember I said that lots of times a fault's not just one fault, it's several little parallel faults? Okay, well, here's two pieces. These are both San Andreas, but there's two of them. You can see they're offset a little bit. And what do we have here? We have an offset stream right here, and this strand right here has created this offset stream. And here are two ancestral channels of it. So this is an interesting area too, and we drive through this. Living on the fault. Oh, I wish I owned this ranch right here, just because it'd be cool. And here's another offset stream. Comes down here, jumps along the fault, and then goes down there. So now I'm just going to show you a few highlights further north. Not going to take you on any detailed trips. This is the San Francisco Peninsula right here. Here's your San Andreas Fault. What are these? Sag ponds. This is Lake San Andreas, for whom the San Andreas Fault is named. Okay, and this is the upper and lower Crystal Springs Reservoir. They're sag ponds right on the fault. They're man modified, of course, but they were there years, hundreds of years ago. They've been there for a long time. This is the San Francisco Peninsula's water supply. And here's San Francisco International Airport right here. Here you can see the fault actually goes offshore in a place called Muscle Rock. The fault comes, here's a huge fault scarp, a couple 100 feet high. You can see the unstable ground here because it's just been sheared and torn up. Look at all these houses up here. Every now and again, one of them falls. And then the fault goes offshore. When you're standing here, you can look northwest toward Marin County. This is Point Reyes National Seashore over here. This is the other part of Marin County right here. This dip in the mountains right here. That's the Olima Trough near Bolinas, and that's where the fault goes. So the fault goes from this scarp right here across the Golden Gate up there. And here it is. This tongue of land, does that kind of look familiar, like a sag pond? Well, it started out that way. This is Tamales Bay right here. Here's your fault. Okay, this is Point Reyes National Seashore over here, Marin County. And a lot of this area right here is made up of a kind of granite called Selenian granite, which is a type of granite. You can just get her name. Turns out the granite here started out in the Tehachapi Mountains. Oh. It was carried that far north. So anyway, here's the north end of Tamales Bay. Here's Bodega Bay, where they film the birds. There's a little chunk of this granite right here. That's Selenian granite too. There's probably Selenian granite connecting these two underwater. This is the northernmost exposure of this Selenian granite. This is the Franciscan Formation, which is a very interesting formation. It's actually ancient seafloor that's been lifted up. California state rock is serpentine. Okay, serpentine, you find a lot of serpentine in here, and it came from the seafloor. Okay, so that's the state rock. The state mineral is gold. The state gem is bonitoite, and all three of those are here because of the fault. Okay, and then going further north up toward Point Arena, fault comes along through here. Now up here, you get north of Hollister, or not Hollister, north of San Juan Bautista, it gets harder to see the fault because you have forests and ground cover. So we're lucky down here in the southern part of the state because we can actually see the fault. But you get further north and it's hard to see, and there are fewer people and fewer roads, and so it's harder to follow the fault up there. But here it is. Anyway, it crosses Highway 1 right here. It goes offshore to a place called Alder Creek in a state park, and here is the headland there, and by now you're experts. Fault comes through here. Notice the green patch. Notice the different colored rocks on either side of the fault. I mean, when you get up there, you look at it, it's beautiful, but you might not look at it in a way to tell you that there was a fault there. But you all know how to do it now. Anyway, it's a beautiful area. From this point, the fault goes offshore again, heads up past Fort Bragg, and then it may or may not come ashore at a place called Shelter Cove, Point Delgada. It's very hard to tell. Thick forest, heavy ground cover. We see a lot of Franciscan Formation there, so we know we're near the edge of the fault, but it may or may not come ashore there. It goes offshore again, or stays offshore. It goes up to Cape Mendocino, bends around, and disappears. By the way, Cape Mendocino is the most seismically active part of California. Okay? The most active fault in California is not the San Andreas, it's the San Jacinto Fault, which is out in Riverside County. That one burps and moves way more often than the San Andreas does. I had a great time writing this book because I got to drive around and see things and all that kind of stuff. And I did it in a regular car. I didn't use four-wheel drive anywhere. Well, a few places, but that's not in the book. Mostly, you can see the fault from one end of California to the other in a regular old car. Okay, so that's the main thing. It's easy to see if you know where to look. Here's what I like best. Man, there are some roads out there where there is no traffic. And if you want to stop in the middle of the road or back up or park your car across the road, you can't. There's just no traffic. Okay? That's one of the things I really like about it, is that you get to places, out of the way places. I love this part, the landforms, and I've only showed you a fraction of the landforms. You get landslides, you get cracks, you get all these other interesting things. If you don't give a hoot about rocks, that's fine. There's wildflower, wildlife, and all that. And here's the main thing. All it takes is a decent car. So I've got a book and a CD to tell you all about it, but start here. Go to my website, okay? Here I have a Google map of the fault. And so you can go to any place along here and zoom in, okay, and see who's living on the fault. And so that's a real good place to start right there. So that's it. Thank you for coming.